All right, happy Monday, everyone. I know we've all been dying to have physics class again. I know I have. It's been, I think, 10 days since our last normal physics class. I think by Tuesday we'll have gone 12 days without like a regular physics class for the full amount of time in our classroom. But today we're going to make up for some of the time that we've missed. So I'll go through 2 of the pages of the notes and then several example problems from the homework. I'll tell you what practice problems you should work on tonight, and we will have a quiz tomorrow when we get back to things. After the quiz, we'll move on with circular motion. That'll be a new part of this unit. But without further ado, here we go. So our next section in the notes is tension. This is on page 9 here. We're going to start off with the question, what happens if I hold a yo-yo by its string? So let's just imagine we've got a string and it's holding a yo-yo. All right, and I'm just holding it there. If it's not moving and its speed is not changing, its acceleration will be 0. So what is its acceleration? It will be 0. All right, and we'll talk about how that ties in later. All right, so tension is the force exerted by a string, rope, or wire. In our lab, it was the force that the string was pulling on to pull the cart. It was also the force that was being transferred from that bottle. Tension always acts along the direction of the string, rope, or wire. There's under tension. Tension applies the same force to both ends or both objects a string is attached to. All right, so we're going to take the example of just a 1 kilogram yo-yo. We're going to be asking, like, what must the force of tension be? So if we've got a 0.1 kilogram yo-yo, we've got the force of gravity on it, and then we've got tension pulling up on it. Because it's not accelerating, we know that the forces have to add up to 0. We know that because of F equals ma. I know it's been a while since we've seen that, but if our acceleration is 0, that means our forces have to be 0. They have to add to 0 as well. This means whatever we calculate for Fg, tension has to be the exact same. So let me go about finding the force of gravity. That'll be equal to m times g. Again, that's in your formula sheet. It'll be on the AP test formula sheet as well. So the force of gravity is my mass, which is 0.1, times g, which is 10 meters per second squared. So the force of gravity is equal to 1 Newton. Okay. This tells us that tension also has to equal 1 Newton. All right, if gravity is pulling down on it with 1 Newton, tension has to be pulling up on it with 1 Newton. All right, and then in this example, let's say that my finger is holding the other end of the string. If the tension in the rope is pulling the yo-yo up with 1 Newton, then it also has to be pulling my finger down. Okay, so when you hold something by a string, that string is pulling the object at the end up, but it's also pulling your hand down. The string is also applying 1 Newton force to my finger. All right, now we're going to go into the spring force. A lot more straightforward. So the spring force comes from stretching or compressing a spring past its equilibrium point. The equilibrium point is the natural length a spring has. Okay, so if we look at a spring, I'm going to take apart this pen just because there's a spring inside. I think I should be able to get the spring out. Shoot. There we go. All right, here's the spring. Okay, this is its equilibrium point. If I pull it like this, right, if I extend it like this, it's going to want to return to that equilibrium point. If I compress it, so if I squeeze it, it's going to want to return to that point. So whether I squeeze it, it's going to want to go back, or whether I pull it, it's going to go back as well. Okay. The spring force acts to return a spring to its equilibrium length. The magnitude of the spring force depends on how far the spring has been stretched or compressed. All right, to get the spring force, this is our equation. So we've got the force from a spring is equal to a negative. We'll go about why that's negative soon. K, which is how strong the spring is, it's called the spring constant, times delta x, and that's how far the spring has been moved from equilibrium. Okay, so we basically take how strong the spring is times how far it's been stretched. K is the spring constant, and delta x is the displacement from equilibrium. All right, we can figure out how many or what units K has doing this. So the units of force will equal the units of K times the units of delta x. So let me put in the units that I know. So I know that the newtons is the unit for force. So this is force. That'll equal whatever K is times delta x. Delta x is measured in meters. So if I want to figure out the units for K, I'll divide both sides by m here. And I can see that my units for K have to be newtons per meter. All right. So K has units of newtons per meter. The negative sign shows that the spring force acts in the opposite of the direction the end of the spring has been displaced. All right, and we'll show that here through a series of pictures. So first, we're just going to draw a spring at equilibrium. So we're going to say this is some mass here. This is the equilibrium point. All right, if I stretch this spring, like this, I would say my delta x, so my displacement from equilibrium, is positive. However, my force that the spring is applying on this box, if I've stretched it this way, so like if I take this spring and I stretch it this way, the force that it's applying on this end is back towards equilibrium. So if delta x is positive, so if I've moved the box in the positive direction, the spring is going to pull the box back in the negative direction. That's what this negative sign here in the formula is telling us. So if delta x is positive, then F is negative. The same is true in reverse. So if I squeeze the spring, then delta x is negative because I've moved the spring in the negative direction, but my force would be positive because my force is pushing in this direction. So F is positive. All right, here's an easier example problem. So if I hang a 4 kilogram object from the ceiling with a spring that has a spring constant of 100 newtons per meter, how far will the spring stretch? Okay, so here's our setup. Got a 4 kilogram object. All right, 4 kg. Hanging from the ceiling with a spring. All right, so I've got it's hanging from the ceiling with a spring. How far will the spring stretch? All right. So I've got the force of gravity is pulling down on it like this. And then the thing that's counteracting that is the spring force. So the force of a spring. Okay, the things I know M. I know Fg equals mg. So M is 4, Fg equals mg. And a K is equal to 100 newtons per meter. I'm looking for how far this thing stretches. That's going to be delta x. Okay, so first of all, I'm going to say that the force of gravity and the force of friction are the same. Or sorry, the force of gravity and the force of the spring are the same. So Fg equals Fs. Force of gravity is mg. That's equal to the force of the spring, which is negative k delta x. Okay, now I'll plug in all the numbers that I know. So m is 4, g is 10, negative sign is negative, and then we got 100 for k. We're looking for delta x. All right, this one's going to be pretty straightforward. To get delta x, I'm going to divide by negative 100 on both sides. So divide by negative 100, divide by negative 100. 40 divided by 100, that will be 0.4. Negative 0.4 is equal to delta x. This will be in meters because delta x is measured in meters. Okay, again, and then, I can go backwards and check my work if I want. So I can do 0.4 meters times 100 newtons per meter. That gives me 40 newtons. 40 newtons exactly cancels out the force of gravity. So that all works out. Okay. All right, we're going to go back to the tension portion When I was first recording the video, I noticed that my explanations of these two example problems were subpar. So I cut those out originally. I'm going to go through them now. So I'll do these two example problems, and then I'll give you some example problems from the packet of problems. I'll have that posted online. And your homework for the rest of the day today will be to finish all of the ones that you've not done on that packet. They should be pretty straightforward. They're all broken down into steps with some scaffolding, so should be pretty easy to follow along. Okay, so we're going to go through these two example problems. First one, an 18 kilogram stoplight is suspended over a road by two wires which each form a 10-degree angle with a horizontal. What is the tension in the two wires? So let me draw this stoplight first. So it looks like that. You know, it's going to be hanging over a road, suspended by some wires there. It's telling us that these wires make a 10-degree angle. Okay, so if I draw an angle with the horizontal, that'd be 10 degrees. 10 degrees. All right. Somehow, the tension from these ropes is holding this stoplight up in the air. Okay. When we see these aren't moving. They're not accelerating. That means that all the forces on them have to add up to 0. So there's gravity that's pulling on them. And then they've also got this tension force. So this would be the force of tension. And this would be another force of tension, right? These are both strings that are pulling on this thing. Somehow, all three of these cancel out to 0. It's asking us, what does the tension have to be in these strings so that it adds up to 0? So what is the tension in those two wires? Okay. One sort of intuitive thing that we can say is that whatever mass is here, like whatever weight we have, so let me first find the weight. So the weight would be m times g, which is 18 kilograms times 10 meters per second squared. So the force of gravity is 180 newtons. Okay, so there's 180 newtons of gravity pulling down on the stoplight. If we want our forces to add to 0, then we need 180 newtons pulling up on it. That means that each wire has to be holding 90 newtons of force going upwards. Now, we might ask, like, how is there force going upwards if we don't have any like wire pulling directly up on it? And the answer is that these wires, they both have a component of their tension that's in the upwards direction. So what I can do for one of these tensions is I can say, well, look, I can break this tension down into a vertical component plus a horizontal component. All right, what's more, I know that the vertical component of my tension has to be 90 newtons, right? Because the tension on this wire that's vertical plus the tension in this wire that's vertical have to add up to 180. So I know that this side of my triangle is 180 newtons. All right, I'm being asked to find what is the tension in this wire. This might be something you've got to solve for, like, you know, how thick of a wire do you have to use? Or if you're hanging something in the future, like if you're trying to suspend something or tie something down on a truck, this is the type of forces that you have to think about. To figure out this tension, it's going to depend on this angle here. So this is a 10-degree angle. Depending on like what that angle is, that'll affect like what our total tension has to be. You can imagine if it was like a 90-degree angle, if the rope was just going upwards, then we just have a tension of 180 newtons. Sorry, this should be 90 newtons because it's going up. Each of them have to carry 90 newtons. Okay, so I've got 90 newtons pulling upwards, and then I've got some force pulling sideways. Those both add up to the tension if I use Pythagorean theorem. Okay, to get my tension, I can use, I've got my opposite side of the triangle labeled, and I've got the hypotenuse. The trig formula that relates those two is sine, so I can say that the sine of my angle will equal opposite over hypotenuse, which is tension. Then I'm going to solve for tension. Okay, so first let me figure out the sine of 10. So here we go. 10, and then I'm going to hit sine. So 0.173. So 0.173 is equal to 90 over t. To solve for t, I'm going to multiply both sides by t. These guys go away. I get t times 0.173 is equal to 90 degrees. And then I'll divide by 0.173 on both sides. All right, so to get my answer, I'm going to do 90 divided by 0.173. So my total tension in this rope is going to be, or in this wire is going to be 520 newtons. Okay, cool. This makes sense. If we were just going to like hang something just vertically, that takes a lot less tension than trying to like pull those two wires apart like this. You know, you're going to have to put a lot of force on those to be able to pick up this if you've got just a 10-degree angle. The smaller your angle here, the less of the components in the vertical direction, the higher your tension is going to have to be for this type of problem. Okay, the second one also involves vectors and components. So it says, if you hang a rosary from your rear view mirror in your car and you accelerate at 2 meters per second squared forward, at what angle will the rosary hang? All right, this one has to do with forces and acceleration. We've got like tension in there. We've got a mass on a string, essentially, but they don't give us the mass. And so this is a great piece of advice. If they don't give you mass and they're asking you to find something, some quantity, just say that mass equals 1. All right, because the mass will cancel out at some point and you'll be fine. All right, so we're going to do this problem as in, like, we got a car. It's accelerating forward at 2 meters per second squared. Inside the car, we can imagine if we were hitting the gas and we had something hanging from the ceiling, that thing would move from being just like a mass like that to it would go over here, right? It's going to be displaced by some angle. So let's call that theta. So really, whenever you hit the gas, instead of something just hanging straight down, it's going to move backwards. So this is the picture that we want to think about. Is we want to think about a mass that's kind of sort of like flying back in the car. All right, and we got to think about what forces are acting on this. So we've got tension that's holding it to the ceiling. So this is tension, and we've got gravity pulling down on it. All right, to solve this problem, it's asking us to find what is this angle. So it's trying to tell us like, what is this angle right here? All right, I'm going to draw my free body diagram a little bit bigger. All right, so we got this guy. We're pretending a rosary is just a mass on a string. For other problems, they'll just say a mass on a string instead of a rosary or something like that. But we've got tension, we've got gravity. All right, tension, I can write tension as this force going sideways plus this force going upwards. I'm saying that once I hit the gas and I'm accelerating, this is just going to stay at this angle. What that means is that it's not moving up or down in this direction. So it's this pendulum isn't moving up or down. However, this the mass will be accelerating with the car. So the mass is going to accelerate forward with this acceleration. In terms of its up and down motion, however, the force of gravity will be canceled out by this component of tension. So this will also be the force of gravity. And this will be whatever acceleration it takes to move that car forward at 2 meters per second squared. Okay, so, and we're looking for this angle again. Cool. To get the force of gravity, I'll just do Fg equals mg, which is equal to 1 times 10, to 10 newtons. All right. So in my triangle here that I'm trying to solve, I can say this is 10 newtons. All right. In terms of this mass, it's accelerating with the car. It's hanging at that angle because this tension is essentially pulling it forward. To get my force, I can use Newton's second law. So force is equal to mass times acceleration. This is my acceleration, right? My mass is being pulled forward at 2 meters per second squared. It's got a mass of 1. So mass is 1, acceleration is 2. I get a force of 2 newtons in this direction here. That's what the force has to be on this dot in order for it to move along with the car. Again, we're thinking of this as like a mass on a string. Think of it as like a yo-yo or like a rosary hanging from a rear view mirror. All right, at this point, we've got everything we need in order to find this angle. So in this triangle, we've got 10 on this side, we've got 2 on this side. We can use our trig formulas. So I've got opposite the angle and I've got adjacent. The one that relates those two is tangent. So tangent of my angle is going to equal opposite, which is 2, over adjacent, which is 10. All right, I'm going to solve for theta. So I'll take the inverse tangent of both sides. So I get theta is equal to inverse tangent of 2 over 10. So tangent negative 1 of 2 over 10. I'll try that out in my calculator here. All right, so 2 over 10 would be 0.2, and I want to take the inverse tangent of that. So I press that button, I get 11.3. 11.3 degrees. So that will be this angle here. So that rosary will hang at an 11.3 degree angle. Okay, so now I'm going to move on to a couple of the example problems in the homework packet, and you should be good to go. 6 and 16 and 17. I'm going to go through number 7 because it has to do with some math that we did in our last class where we were actually in class when we were talking about constraints. The biggest thing from that was we figured out that the pole of something on a ramp is going to be mg sine theta down the ramp, and the normal force on a ramp is going to be mg cosine theta. Okay, so here we go. I've got a block on a ramp. It doesn't tell me the mass of the block, so I'm going to say m is equal to 1 because it's asking me for, a number for acceleration. If it was asking me for an expression, I'd have to leave everything in terms of variables, but it's just saying what's acceleration going to be in terms of a number. So I'll say m is equal to 1. Force of gravity down the ramp, that's going to be mg sine of theta. It says our ramp is a 40-degree ramp, so this is 40 degrees. This is my 1 kilogram thing. It's going to be sliding down this way. So that's the force going down the ramp. Mg sine theta will be 1 times 10 times sine of 40. Okay, 1 times 10 times sine of 40. I can do that in my calculator. All right, 10 times, oops, let me click this. All right, let me do sine of 40. So 40, take the sine of that, and then times 10. Times 1 is equal to 6.42. Equals 6.42 newtons going down the ramp. So we've got 6.42 newtons heading down the ramp. What about the normal force? The normal force is mg cosine of theta. All right, so mg times cosine of theta. I got to do cosine of 40, and then times m times g. All right, so mg cosine theta will be m is 1, g is 10, cosine of theta is 0.76. So this is going to be 7.6 newtons. Okay. So we got a 7.6 Newton force. That's the normal force. That's like this direction. It's asking what is the force of friction on the ramp? Okay, to get friction, the force of friction is equal to mu times the normal force. I get that from my first page where I got the formulas. Which is over here. Right here. Okay. So this first page, force of friction is mu times n. So I just take mu, which is my coefficient of friction, times the normal force. I've already got the normal force, which is 7.6 newtons. Okay, so force of friction will be coefficient of friction, which is mu. This is mu. So 0.2 times the normal force. So 0.2 times 7.6. 0.2 times 7.6 would be 152 with the decimal point there. So 1.52 newtons. All right. So gravity is pulling this block down the ramp. Friction is resisting that pull with 1.52 newtons. To get the total force on the block, I know that this block isn't moving in the up or down direction in terms of like this ramp. It's not coming off the surface. It's not going through the surface. It's just moving either in the up or down direction of the ramp. The two forces that are in that direction, we've got gravity pulling down the ramp. We've got normal force pulling it back up the ramp. Okay, the gravity is going down the ramp, so we'll say that that's 6.42 newtons going down the ramp. All right, we're going to subtract the force going up the ramp. You could either do 1.52 minus 6.42 or 6.42 minus 1.52. Either way, you're finding the difference of these two forces because they're going in opposite directions. 6.42 minus 1.52, that will give us 4.9 newtons. For its acceleration, we're going to use F is equal to ma. So we get force is 4.9 is equal to m times a equals 1 times a. To get acceleration by itself, I just divide by 1. So 4.9 is equal to a. This would be meters per second squared. So 4.9 meters per second squared. That's what I did there. Okay, cool. Number 8 is similar to that, so you can work through that and make sure you know how to do that. For number 9, fairly straightforward. You got something hanging from the ceiling, so you got gravity pulling down on it. Tension cancels that out. For number 10, same deal, except for they give you the force. They're asking you, what is the maximum mass? So you're kind of doing this in reverse. So first, you're going to say the maximum force of gravity would have to be 5,000 newtons, and then you got to figure out what mass would cause that force of gravity. Number 11 is fairly long, but if you work through each step, we'll be able to get to our final answer. First, we got to think, what is the object's acceleration in the y direction? So is it moving up and down? It is not. So that means the net force in the y direction has to be 0. All right, so now we're going to figure out all the forces in the y direction. So we've got the force of gravity on the object. All right, we can do that by doing 25 kilograms times g, so that would be 250 newtons. What is the upward component of my pulling force? All right, so another component on my vertical direction is this part of me pulling on it. So I've got an upward portion of my pulling force and a sideways portion of it. Okay, so the upward portion of my pulling force would be 100 times, it looks like if this is 30 degrees here, sorry, I can make sideways portion here, upward portion. So the upward portion is going to be opposite of 30. Okay, so that would be 100 times the sine of 30. All right, that's going to be 50 newtons in the upwards direction. I can think of this as like a negative 250 newtons because it's pushing downward. This would be a 50 newtons. What must the normal force be so that the forces in the y direction add to 0? So I've got 254 newtons going downwards, 50 newtons pushing upwards from this pulling force, and then the floor has to provide the rest of the force so that they all cancel out. So if I've got 250 downwards, I need 250 upwards. I've already got 50 newtons upwards, so I need another 200 newtons of force from the ground. That way, if I add the force from the ground plus the force that I'm pulling up on it with, that'll equal the force of gravity, and it won't be moving up or down. What is the force of friction given that normal force? So to do that, we do mu times normal force, which is just 0.15 times 200, which is 30. What is the sideways component of my pulling force? Well, the sideways component of this would be this portion right here. So that would be adjacent. I can do 100 times cosine of 30 to get that. Again, I'm thinking about breaking this vector down into a horizontal component, a vertical component. I use sine to get my vertical component. I'm using cosine to get this horizontal component. That'll be 86 newtons. Net force in my sideways direction will be 86 in this direction. Friction is pulling back on it with 36 newtons. So 86 newtons minus 30 newtons. This is all going to get me 56 newtons. What is the object's acceleration in the x direction? I got to do F equals ma. I plug in this force here. So that's 56. That's equal to m, which is 25 times a. I'll divide both sides by 25. I'm going to get a is equal to 56 divided by 25. 2.24 newtons. Okay. All right. 12. This one's fairly straightforward. This is just talking about, it's very similar to the one in the notes. So if you've got 50 newtons of force on one end of something, like how many meters will it stretch? We know force, we know K, we're looking for delta X. This next one is also a spring problem. Squeeze 0.1 from equilibrium. That'd be our delta X. It's got a spring constant of this. How fast would it accelerate a 4 kilogram object? So first find the spring force, then what is the acceleration? For acceleration, again, once you've got force, the thing that ties force and acceleration together is Newton's second law. So F equals ma. All right, last page, let's see these ones. Okay, I'm gonna do number 14. I'm gonna leave number 15 for you to do. So your responsibility is to have the rest of this problem set done for Tuesday. We're gonna start off Tuesday with a quiz, which is problems from this packet or from the example problems in this lecture video, like from the notes. So I'll do 14, and then we're gonna call it good for that, and I will see you all tomorrow. So 14, on a dry road, the coefficient of friction between the tires of the road is around 0.7. The car is traveling at 30 meters per second. What is the minimum stopping distance of the car? All right, first, let's find the force of gravity on the car. All right, again, don't know our mass. We call m equal to 1,000, or we can call m equal to 1. It's not going to change our answer because these things are going to cancel out at the end. So I'm just going to say m is equal to 1 for my car. So the force of gravity on the car will be m times g, which is 1 times 10, which is 10 newtons. All right, normal force on the car has to be 10 newtons as well. Force of friction on the car, that's mu times the normal force, which is mu is 0.7, so that'd be 0.7 times the normal force, which is 10 newtons. So that's 7 newtons of force. What is the acceleration of the car? To get acceleration from a force, I do F equals ma. So 7 is equal to 1 times a. Divide both sides by 1. See, that's where I'm dividing by the mass. If I used m equals 1,000, this would be 1,000 times bigger. That'd be 1,000 times bigger. That'd be 1,000 times bigger. But I'd be dividing it all by 1,000. So I'd get back to the same answer because mass cancels out. Then I get A is equal to 7 meters per second squared. All right, use the last kinematic equation to find the distance the car travels between its initial speed of 30 meters per second and its final speed of 0. Great, that one is v final squared equals, we just call it v squared is equal to v initial squared plus 2a delta x. So v final is going to be 0 because it stopped. V initial is 30 meters per second. 2 is just a 2. A is 7. And delta x is what we're looking for. All right, great. So we get 0 is equal to 900 plus 14 delta x. I get negative 900 is equal to 14 delta x divided by 14 divided by 14. And we get delta x is equal to 900 divided by 14. All right, 900 divided by 14 is 64.3 meters. So that's how far it would take to stop on a dry road. As a note, I'm getting a negative answer for this. The reason I'm getting a negative answer, and I should have gotten a positive answer, is my acceleration is really against the direction of motion because I'm slowing down. So technically this would be a negative number. That would make this a negative number. I would be dividing by a negative 14 here. That would turn it into a positive number. At the end, just look at it and think, does it make more sense for it to be positive or negative? The sign for the final answer really doesn't matter too much. Okay, that's going to be it for today. Good luck with these problems, and I'm looking forward to seeing you tomorrow. And we'll be starting circular motion, which also has to do with forces, and we'll be referencing some of this. But make sure you do these problems and be ready for the quiz tomorrow. So have a good one, everybody. Don't be too stressed about the quiz. It'll be fine. You can retake it if you do badly. But if you've watched these videos and worked through all these problems, you're going to be fine.